Welcome, folks. This is the recap of ARC AGI Prize 2025. I'm going to do a few things today. I'm going to walk through the leaderboard. There's not a whole lot that we can say because a lot of the submissions have not been released publicly as to what they're doing just yet, although I believe quite a few will. Nonetheless, there are a few highlights, and then I'm going to take most of this stream to walk through the TRM approach, tiny recursive models, that I submitted to the competition this year. It scored 6.67%. So quite a bit off the top score, but even getting into single digits is not that easy on ARC AGI 2. And the TRM paper, when it came out, it was a significant open source advance. There's a possibility it's been used by some of the leading scores. I'll talk a little bit about that. If you have any questions, we're live on YouTube, Twitter, and also on LinkedIn. Just put in questions into the comments. I think there's a little bit of a delay, so give it a little bit of time before it comes through to me. And I will then try to respond, just take the questions as we go through. So first off, taking a look at the leaderboard here. Let me zoom in a little bit. In first place, NVARC, Giotto AI, who had been leading for most of the tournament. Then the Architects, who were the winners from last year. Minds AI at Tufa Labs actually were the highest score last year, but because their solution was not open sourced, the official winners were the Architects. And the North Stars, I believe, is a new team. Not sure if any of those submitted last year. And Guillermo here, who placed well in last year's competition. I'll talk a little bit about him and his approach. All the way down here, you can see the Trelis score, 58. And actually, this was as high as 14 at one point, but I believe there was some notebook that was made public and a lot of people submitted the notebook. So there were a lot of scores that are in and around the 6 to 7 range, as you can see right here. Now, it's worth noting that these are the scores on a semi-private set. The way that the ARC competition works is there are 240 private questions. Actually, 120 of them are called semi-private. And during the run-up to the competition, you can submit, and your solution, your notebook will run on all 240, which is we'll get to later. It's actually important when you're designing a solution notebook. It will run on all 240, but the scores will only be revealed for 120 of those tasks. And that's what you see here. You see the semi-private scores. But what counts ultimately is your score on the private set, which is not disclosed at all to minimize any chance of leaking. And those other 120 problems that your submission will also have been run on are the ones that count. So we don't really know who the winner is yet. It won't be disclosed until December 6th. I presume the organizers kind of know because the notebooks have each been run on all 240 tasks, but they have to check, first of all, that the description will be open sourced, which is required to win the prize. And I assume there are some, well, I don't assume, but perhaps there are some other checks that mean they want to take until December 6th, which is kind of a long time to wait. And as you can see, there's not a whole lot of difference here, 27.64 versus 27.08. I was reading a little bit more here from this man here, JF, I think his first initials. And he explained that actually they had a better submission that did not go through because there was a big queue of notebooks. I'll talk a little bit later about submission process, but on the final day, which was Monday, you had to have your notebook complete before midnight for it to be possible to be considered. But on Monday morning, at least Irish time, there was a backup of L4s, which are the GPUs that you use. And it took hours to get submissions accepted. I didn't get my last submission accepted. I actually shortened the runtime on it, which adversely affects the score. So it got submitted in the end. It was only started running at about 4 p.m. So it had about 6 hours to run. But this means that probably NVARC had an even better score. I don't know, maybe 30, maybe 35. And because let me just show you this here. This is from Guillermo on Twitter. He put together this nice little app that shows you the evolution of the scoreboard as you move through dates. And look right here in blue. This is the score of NVARC, which is just going through the roof. Clearly, they have unlocked something. Sorry, my screen is just stopped sharing. They've unlocked something over the end here of the competition. And pretty much not every submission, because you can see a few in a row here. Wait, sorry, I'm not sharing my screen just yet. Here we go. Share screen. Sorry, this might be an issue for the rest of the stream. I had it in a previous one. But yeah, here's the line. And you can see performance improves very fast. So clearly they found some kind of unlock. Not clear if it's a TRM model. There were some comments on Twitter that JF had given the thumbs up to a lot of posts about TRM earlier on, so it could be linked. The fact that TRM is able to score 8 or even 10% on a pre-trained model I got shows you that it has potential to score. Maybe there's a direction of unlock. Maybe it's training a larger model. Maybe it's training a smaller model. I would tend to guess maybe larger, but could be smaller. And if you do find a hyperparameter that allows you to scale, maybe you can just keep pushing in that direction and keep improving your score. So, I mean, that's a very loose explanation, but that might be my guess. I want to show you the page where the Trelis submissions are. It's right here. So actually the highest score was back about 2 weeks ago. It was when I submitted post-training of a TRM model, and I'm going to walk through every step of that today. And since then, unfortunately, I wasn't able to improve on it. I tried a lot of ablations, making the model smaller, making the model larger, running with different types of post-training, LoRa, fine-tuning, full fine-tuning. Full fine-tuning worked the best, by the way. I also tried freezing part of the model for part of the fine-tuning, freezing different amounts. I tried adding some noise to the input grids. I tried training the base model for longer, but yeah, I just wasn't able to improve on the score. So the best 2 scores will be the ones that are counted for the purpose of the private leaderboard, which is the one that counts. So I don't know. I expect I'll probably be in a similar position on the private leaderboard as on the semi-private leaderboard, unless there's some reason that the other solutions or my solution are overfitting to a different degree. Now, before this TRM approach, which was roughly around here, sometime in mid-October, Lewis and I were focused on a Python program writing approach. And we actually submitted a lot of Python program application attempts. So here, all the way back down to here, we really tried a lot. We submitted a Python approach. And I think the top score we scored with that was 1.67. Now, I'm going to talk about that tomorrow. I have a research write-up that should go out later today. So I'm going to focus today on the higher scoring approach of the 2 that we had, which was the TRM approach. And here's Simon with a question. Thanks also for tweeting out this live stream, Simon. Appreciate that. What naming convention your submissions do you end up with? Yeah, really bad programming practices here. I suppose what are my naming conventions? Okay, let's go through one of them. So let's go through this one. L4, which means I ran the submission on an L4, which is actually important because if you run a submission on a T4 and submit it, it will actually run on a T4, which is not obvious, but problematic because the T4 will have way less flops and it's not going to achieve the same performance. So L4 means the GPU, TRM means time recursive model, 15 KE means I post-trained for 15,000 epochs, 256 EA, that means evaluation augmentations. No, it doesn't correspond to a branch or commit, which probably would be useful. So I say evaluation augmentations because I modified the TRM code to distinguish between augmentations used during the training and post-training and between the number of evaluations used for inference. And the reason is because compute is limited, you can reduce the number of augmentations during inference in order to reduce the time to run inference. So while maintaining the same number for doing the post-training, which is beneficial for diversity. So that's a code tweak I made, and that's why I say not just augmentations, but evaluation augmentations. And then this is my learning rate, 1E minus 4. I also tested some at, I think, a slightly lower rate of 5E minus 5. But as you'll see in some of the plots I'll show, there's not a huge amount of difference between those. So what I want to do is talk a little bit about the process of submitting here, going all the way from pre-training the TRM model, then post-training, and I'll show you how I simulate the post-training outside of the competition environment. And then I'll show you very briefly the submission itself and what it looks like. In fact, maybe I'll just show what the submission looks like first, kind of walk through this. It won't all make sense, but when I come back around to it at the end, it'll probably help to give a bit of grounding. The other thing I want to do is very quickly go through the research paper that I've released. You can find it. It'll be on archive soon, hopefully, if it gets accepted. You can find it at trelis.com/RKGI2. and it is a proper write-up describing everything that was done in TRM. And I suppose to briefly describe what I did is just to say that I took the tiny recursive model approach that Alexia had developed and that scores 8%. I actually replicated that pre-training and scored 10% on the semi-private set. And then with that model as a starting point, I ran in the competition a post-training process for just 12.5 or 15,000 epochs, followed by running evaluation for about 256 or 512 augmentations per task. And I'll maybe show one or two of the key tasks here. Let me just download and pull up the paper. Bear with me for a second. And now if I just share this here, I should be able to pull up the paper. We can just look at it here, actually. It won't allow me, will it allow me to zoom in if I scroll up here? I'm just going to get the actual downloaded paper and move it across into the vision here. Okay. So my first step is to take the pre-trained model, and sorry, this is a bit difficult to view. Here we go. Yeah, so I take the pre-trained model and I actually repeated the training that Alexia had done, and I actually score a little bit higher. So you can see on the graph up here, this is the evolution during training of my accuracy pass at 2. Pass at 2 is the way that the competition is scored. So you get 2 attempts on every test output grid, and the best one counts. The competition will pick the best one. So here what you can see is in black rather, this is the pass at 2 with the number of training steps, which goes up to about 700,000 training steps, which corresponds to 100,000 epochs, which is the same as the original paper. So my pass at 2 score gets up to around just above 10%. Actually, Alexia's model gets to 7.8. So for some reason, that's actually not entirely clear. This model scores a little bit higher. The only difference in the model, and I'll show this in the repo, is that it uses 4 lower cycles of recursion instead of 6 stated in the paper. But interestingly, the repo itself has got 4 lower cycles, and everybody else who has done replications has also used 4 lower cycles. So it's a bit unclear exactly where the higher performance. Now, it's not that much higher, 10, 11 versus 8. So it could well be within the realm of noise. Now, something interesting here is if you look at pass at 1000, which is not how the competition is scored, pass at 1000 scores a lot higher. It goes up to about 22%. So it shows you that the model is fundamentally able to reach correct answers for 22% here, but it's not able to convert that into a pass at 2 score. So it doesn't know which ones are the correct ones. Now, the upward slope here on these curves suggests that if I just pre-trained for longer, maybe I would have gotten an even higher score. And I think that's possible. One of the problems is when I finished this training, I shut down the pod, I saved the model, but I didn't save the data set. And if you don't save the data set, the way the TRM model works is it's got a mapping between tasks and indices that become task embeddings. And if you throw away the data set, you lose that mapping. So you can't restart with your embeddings mapping to the data set, which means you need to reinitialize the embeddings. So actually, if you continue pre-training and you didn't use the same data set, and I mean the same generated data set with augmentations, not just the raw tasks. If you don't have that augmentation data set, you're kind of restarting, you are restarting the embeddings from scratch. And so when I did pre-training after this by reinitializing the embeddings, which you also might think could somehow help, because sometimes restarting things helps, but it hurt. It didn't give me any better performance. But if I could go back in time, I would have saved the data set here. I'll show you how to do that later. And it would have allowed me to continue pre-training, and who knows, maybe I would have gotten a little bit better performance. Either way, I took the model here from this last step, and this was my best submission. And then I basically just fine-tuned that during the competition. And you can see the fine-tuning happening here. Actually, I looked at a few different ways, and these fine-tunings I did offline. Now, you should be wondering, how did I test this post-training offline? Because this model, the first model, the pre-trained model, it was trained on ARC AGI2 training tasks and the train examples from the evaluation split, and also concept ARC, which is a set of 160 tasks. Because I put the evaluation set in the training, which is how Alexia does it in her original paper as well. And this makes perfect sense, by the way, if you're trying to train to then test on the evaluation test examples. This, unfortunately, will contaminate any test you want to do of post-training, because in post-training, what you're trying to do is bring a model that has been trained on problems A, and then you're trying to train it a little bit more on problems B. But in this case here, I've already trained it on all the problems in the pre-training. So yeah, the train examples from evaluation are already in the model. So how did I get around that? That's what you should be wondering. And the answer is actually, it's common, well, in the original paper and also in replications, although not in my replication, to run TRM not just on ArcAGI2, but also to run it on ArcAGI1. And there's a lady who I've quoted in the tweets who redid a replication and published her model for ArcAGI1 tasks. And because I have that model, I can use it, which has been trained on ArcAGI1, to then run post-training on ArcAGI2. So actually, what I'm going to show you now, which is the plot of post-training, and it's really my simulation of what post-training can do, it's actually a plot using a pre-trained model from ArcAGI1, which I'm then going to train on ArcAGI2 eval tasks. So let me just put the screen up here. And you'll see, first of all, the number of training steps is far less. And what I should have said at the start, or towards the start of the video, is that the reason TRM doesn't work off the bat for a competition, for ARC prize competition, is just because the number of steps you need to train it are way too large. You need to train it for 48 hours on 4 H100s. In the competition, you've only got 4 L4s. A H100 is about 8 times the BF16 flops of an L4. So you've got a factor of 8 difference there. Plus, training for 48 hours is 4 times the competition limit of 12. So you got a factor of 4 there. So very roughly, you've probably got a factor of 32 insufficient compute during the competition. Now, you could argue that during pre-training, there's 1,280 tasks that are used if you use ARC AGI2 training plus eval plus concept ARC. And there are actually only 240 tasks at submission time, 120 semi-private and 120 private. So you could argue that with that smaller data set, if you fully pre-train, that's only about a quarter to a fifth. So maybe instead of being 32 times off, you're actually closer to maybe 8 to 10 times off. Nonetheless, you're probably at least a factor of 10 too small in terms of compute to do a meaningful pre-training, with the caveat that you could find some better hyperparameters or model design, and maybe that's what NVARC or some of the other submissions did. That just allows you to train in with less compute. There's this concept of being chinchilla optimal, so finding what the optimal size is to achieve the best score. And I don't know what the best model size is. I tried a bit smaller, I tried a bit bigger, but I didn't run the models out for 2 full days. I probably regret that now. So yeah, anyway, if you try and run the original TRM, it's not going to fit in Kaggle. And that's what motivates doing this post-training here. I'll describe this in a second. Just a question from Simon. Yeah, this is another problem. So the ArcAGI2 eval set contains 6 tasks. Well, I don't know if this is what Simon's referring to here. Let me make 2 comments. So ArcAGI1 has got 400 training and 400 eval tasks. Most of those 800 tasks are included in ArcAGI2 training, which is a 1,000 task data set. So there's a bit more than 200 because some of the ArcAGI1 tasks are left out, but there's a bit more than 200 completely new tasks in ArcAGI2 training, which brings you to 1,000 tasks. Mostly 800 from ArcAGI1 plus some extra tasks. So you've 1,000. Then you've 160 concept ARC tasks. And then there are only 120 public eval tasks. So when you add those up, you've got 1,280 tasks. Now, there are 6 of the ArcAGI1 eval tasks that are also in ArcAGI2 eval, which is annoying because it means if you have a pre-trained model on ArcAGI1, it's contaminated from a post-training perspective on 6 tasks from ArcAGI2. So actually, this graph here I'm showing, it's maybe artificially shifted up a little bit because it benefits from pre-training, because there's contamination of the tasks. And I did realize this later, and I made a data set that omits those tasks. You can find it in the public repo. So if I was going back and doing this again, I would use ArcAGI2 evaluation clean, which is 114 tasks. It's the 120 minus the 6 contaminated tasks. Okay. So this also is a relevant point here. So the reason I tested out post-training, this is quite early in TRM. TRM paper had come out. I'd kind of researched it. I was thinking, can I post-train this? And my first thought was I should LoRa train it, because that's what you always do. So I went about thinking, well, what model can I LoRa fine-tune to see if I can get better performance? And I went through the logic I described, which is that it doesn't make sense to use ArcAGI2 model because that's already contaminated. So let's use the ArcAGI1. And if I can post-train that, that's really exciting, because it should be a weaker model than ArcAGI2 because the quality of tasks it's pre-trained on are worse. Now, actually, having done all this now, I think the ArcAGI1 model is not that much weaker than the ArcAGI2 model, which is also a bit surprising. But yes, for this reason, if I had failed at that experiment and post-training the ArcAGI1 model and ArcAGI2 was useless, if this had scored zeros, I couldn't have ruled out that post-training was a good idea, because I might have just concluded the ArcAGI1 model was not good enough. That didn't happen. Actually, post-training the ArcAGI1 model was good enough to give me a signal. So when I saw this, and I saw that with some training steps, I could get a few percent, I was thinking, okay, great, because if I now just submit this, but I submit it with the ArcAGI2 model to the actual competition, then I should score higher. And I did. I scored about 6.67. So, you know, I scored a little bit higher, which is kind of what I expected. So this experiment ended up being useful. Now, there are a few different things. I said initially I would try to do post-training with LoRa. And so I did that. It was probably one of the first things I did. You can't really see it too clearly, but it's scoring 0 down here. And I quickly realized doing LoRa was definitely not going to work. And the reason is because the embeddings are randomly initialized when you see new tasks. So I see this question on GitHub on the original TRM repo a lot. And the question is, what happens if you use TRM on unseen tasks? And the answer is the embeddings. So think of TRM as 2 parts. There's the embeddings and there's the model. The model is 7 million parameters. And then you have an embedding for every task, not only every task, but every augmentation. So you actually have 1,000 embeddings if you have 1,000 augmentations defined for each task. And when you start on new tasks, you reuse the trunk, but the embeddings are initialized by default to the mean of the pre-trained model's embeddings at the end of pre-training. So if you only do LoRa training on linear layers in the trunk, your embeddings are just wrong. So at a very minimum, you need to train LoRa plus embeddings. And actually, this is misleading. It's not misleading in the text, but LoRa here actually means training with embeddings. So training the embeddings and training LoRa. But even still, when you train the embeddings in LoRa, the performance is bad. And if you just train the embeddings, which is down here, the performance is also bad. The performance is only starting to improve when I started to do full fine-tuning. And that's the top curve here. And there's an other curve that shows where I only train the embeddings, either for half or for a quarter of the steps, and then I train everything for the rest of the steps. And it's just too noisy to really say which one is better. A lot of my submissions froze the embeddings for a quarter or a half, but here there's no difference between training everything for all the epochs or training just the embeddings for some and then training everything for the rest of it here. So this is kind of the demonstration that full fine-tuning seems to be necessary. You can't just do LoRa, you can't just do embeddings. And what I want to show you here, since we have the benefit of being on a computer and not just reading the paper, I want to show you the weights and biases report, because it gives you a bit better picture. Let's go to 1B, and I'm going to find the project. And you'll see why this gives a little bit more color than just looking at PASA2 and PASAT 1000. These are public, by the way. I think it should be this one. They're linked in the paper. And this is unfortunately not the one I want to show. And let me go back here. You can find the original pre-training run, which I will actually go through because that's it's instructive to see what's happening there. And what I want to show you is the post-training and what the scores do in that case. Let me see. Okay, great. So this is what the scoreboard looks like. I'm actually going to show you the pre-training first, and then I'll show you the post-training. And this is the weights and biases view you're going to get if you train a TRM model. But I've added in a few extra views as well. So we're going to take a look at the pre-training, which is this purple curve here. And then I'm going to show the post-training. So as I showed in the paper, the pre-training goes to a score of about 10 to 11. If you look at pass at 1, the score is lower. If you look at pass at 1000, the score is 0.2. Now, basically what's happening in the TRM model, and I'm backing up here to what is the TRM model doing, it's essentially massively overfitting all of the examples that you train it on to the extent that not only is the pixel accuracy basically 1 for most of the training, but the exact accuracy is also pretty close to 1. Exact accuracy means getting full grids correct on the training data. So yeah, this is really, really accurate. Also, TRM, it's a recursive model. It will do up to 16 loops, and then within it will do, I think it will do either 4 or 2 higher loops and 4 lower loops. But the outer loops, there are 16 max. And as it learns to stop if it has reached an example. And on the training data, it learns to stop quite well because the average by the end of training is only 1.25 loops. However, and this tells you it's overfitting, if you look at the exact accuracy on the eval example, it's only scoring 0.04 or 0.05. And it's possible to get a higher pass at 2 score because you're, allowing for 2 answers. And it's also not exactly a 1-for-1. When you look on a grid basis, there are multiple examples per task, whereas a task is a compounding of multiple examples. So that's why the pass at 1 is not exactly the same as the grid level accuracy. But suffice to say, there's massive overfitting because the exact accuracy is a lot lower than what it is on the training set. Now, again, this is kind of pointing up, which suggests, well, doing some post-training would probably, or I don't know if it probably would be helpful. I really don't know if it would be helpful. It may or may not. And yeah, while the steps go down, the number of recursions needed go down on training. If you look at the eval data, let's look at the steps here. Yeah, the number of steps basically just stays the same at 16. So we're not generalizing. The model is not generalizing to eval data to understand that it actually has completed the tasks. In fact, it thinks it hasn't successfully completed any tasks, even though it's getting some level of accuracy here. So these are some of the plots. I'll leave you to check them out for the pre-training. And I'm going to show you now the post-training plots, which is originally why I even came over to this screen here. And the reason I want to show you this, I'm going to just highlight full post-training, and I'm going to highlight as well just training with LoRa, if I can find that one. Yeah, LoRa. So here in purple, I've got full fine-tuning, and in hopefully you can see that it's kind of a light blue. Turquoise, I've got the LoRa tuning. And you'll remember in the paper that LoRa scores 0 on pass at 2, but actually it's not quite 0. If you look at the pass at 1000, it is actually having a positive effect. It's just that pass at 2 is even more noisy. It's less noisy if you look at a pass at 1000 metric. So LoRa is actually helping, even though that's not clear in the paper's diagram. I do comment on it, but it's not helping nearly as much as the full fine tuning. So that's the LoRa approach. That's the essence of how I get to the score. I just want to talk about, so when I got to that score of 6.67, I said, okay, what am I going to do now? I felt I had optimized the post-training. I had a pre-train model that got 10. My post-train model got 6.67. It'd be nice if we could get up to 10, but it's not that far off of 10. So the biggest lever I saw was to try and increase the pre-trained model's score by somehow ablating something on the performance of the pre-trained model. I looked at increasing the model size, decreasing the model size. But two even simpler things I looked at were to just train for longer and also to train only on the hard tasks. So training for longer, I simply trained for 200 epochs. And training on hard tasks, I trained on the ARC eval tasks from ARC AGI 2, and I trained on 120 hard tasks, hard defined by GPT-5 Mini from the training set. And I'll just quickly show what I found in the paper when I did that. So I go back here, you can see in table format. Yeah, unfortunately, I did worse on both fronts. So when I expanded the data slightly, it wasn't much of an expansion. I included actually some of Simon's data, who's here on the live stream. There are 50 tasks from a TAMA split. I believe they're of difficulty between ARC AGI 1 and 2, but I was hoping some of those concepts might help. And I also put in some of the test examples from the evaluation split of ARC AGI 2, hoping that more examples there would help. That's not increasing the task number, but it increases the examples per task on the hard tasks. So a slightly expanded data set, but training 200 epochs, I ended up scoring 4.25 on my submission, so I couldn't improve. And then I thought, this is another heuristic in machine learning. If you have a lot of data, sometimes it's better to do more epochs over a hard subsplit or a higher quality subsplit than to do the same epochs over all the data. So I took the hardest 240 tasks and yeah, also performed worse even when doing 1 million epochs. So I wasn't able to find anything that immediately gave me improvement. But that said, the space is so large that you could think about for ablations. If I'd have more seriously ablated a larger hidden dimension or more seriously ablated maybe even a smaller model, things would have been different. And I've described a little bit in the paper some of what I've done there. But what I want to focus on for the rest of this live stream is showing you exactly how I go from pre-training model to post-training and then submitting to Kaggle. And I'm going to work slightly in reverse here, starting off by showing you in Kaggle one of the submissions I made. This is the last submission I had here. And I'll just quickly walk through the notebook. It won't all make sense. Then I'll go to pre-training. I'll show you the repo, post-training, and I'll come back to the notebook. First, just a quick question from Simon. Did you try curriculum learning? Yeah, where you start on simple tasks, medium, and then hardest tasks. So I didn't in the last ablations. It makes sense, but I had just a limited number of things I could try. Each of my final runs cost $1,000. So I was quite limited. And that is why it's quite difficult. That makes it quite difficult working with TRM. What you find is that when you don't run the models for long, you just get a lot of noise and there's not enough gap in performance to say that something is better. So it's really challenging. It's also really challenging because there's so few evaluation tasks. And what you're really trying to evaluate is performance after post-training. So it's like a meta goal. You're trying not to just evaluate a base model, but the base model then after pre-training. Now you could maybe simplify that to saying, I'm going to take the pre-trained model that just scores the highest. That's probably the easiest way to think about it. So yeah, in curriculum, I think at one point I took the model that the 10% model I pre-trained, and then I continued training it on some hard tasks, on ARC eval tasks. But unfortunately, that was ruined by the fact that I had not saved the data set. And so I didn't have the embeddings to kind of restart from. And when you reset the embeddings empirically, it made the performance worse. So short answer is no, but I kind of tried a few things around it. Okay, so here is here is a little view of how I would run the notebook. And actually, I'm just going to edit the notebook and do it as though I'm going to submit. I might even just submit or at least save so you can see what that looks like. I think it might be instructive. The competition, I heard maybe this competition will rerun again this next year, I guess, unless somebody gets 80-something% in the meantime. Of course, there's ARC AGI 3, which is quite different. So a lot of what I'm saying may or may not apply. So here at the start of the submission notebook, I have this line here, which anyone who's submitted or is familiar with Kaggle will be familiar with. It checks whether this is a competition rerun or not. And what that means is well, let me say first, to submit, you actually need to save your file first. And by doing save, it's not just a file save. You actually need to save it. And what that will do is run the notebook with the actual GPU. So it can take some time. Now, in principle, it would take 12 hours if you use the max 12. So what you need to do is have a kind of toggle so that you can save it and allow it to run in some shorter manner, such that when the submission run happens and this environment variable is triggered by Kaggle, this is going to go to true, and then it's going to set your normal run. So you need to kind of set up this proxy run that will allow you to save it and run within 10 minutes. And then when it's actually submission time, Kaggle will turn on this variable and it will run like normal. So first thing I set here is the number of augmentations, which is 1,000. I don't change that. It doesn't affect inference. It only affects training because I adjusted the code to make it that way. If it's a computation rerun, I run for 9,000 eBox. This was my very last run where I had to submit it late because there was a big queue, but this would have been 15,000 or 12,500. And here's the number of evaluation augmentations. So for every task, it's going to be evaluated on 256 augmentations, and majority voting will then pick the top 2 that will be added to the submission file. Now, if we're not in this competition mode here, it's only going to run 8 epochs on 8 eval augmentations. So this is really short, and that is going to allow me to save it within just 5 or 10 minutes. Now, one thing you can do is you can make it a bit longer, and then you can inspect the logs of the saved run, and it will tell you information about how long your run is taking. So actually you end up spending a lot of time, for those of you who haven't submitted to Kaggle, you spend a lot of time trying to time the length of your notebook so that you use maximally the full run time. One way to do that is to set a timeout. I actually didn't use that approach. I just I would actually figure out how long the run is approximately going to take by calculating it in an Excel spreadsheet, actually, and then I would just run it. Now, maybe that's unwise. It's better to use a timeout. Timeouts can be annoying, though. If you want to time out in the middle of training, you anyway probably just have a previous checkpoint saved, so it ends up kind of like, and then you might have to save a lot of checkpoints, and you save a lot of checkpoints. It's going to cost you time. It's going to cost you memory. So there's a whole set of trade-offs here. But basically the way I do it is specifically, let me show you specifically what I do. I go to run pod, actually. So I go to the repo, and this is now public. I click on this affiliate link that brings me to a template, and I go to L4s, and I hope that nobody else is using the L4s. Currently they are, so I can't do this. But sometimes there are 4 L4s here, and I would run on these L4s, which is the exact same as the competition environment. And that would allow me to time how long things take. Now, I could run the full 12 hours, but often I'll just start the training. I'll look for the TQDM, the kind of indicator of how long the training is going to take. And that will give me an indication of how long training takes. Let me actually show you what this looks like. Arc runtime. And yeah, I'm just going to reveal here how there are probably way better ways of doing this. But here are some little tests. So I'll say, okay, my base run, and here this allowed me to calculate 9,000. My base run is 12, well, let's say 15,000 epochs. I'm going to run 256 augmentations. And when I measure this on Kaggle, what I'm going to do is, when I measure it on RunPod, I'm going to actually measure 15,000. So I'll set up a run of 15,000. I'm only going to measure 64 augmentations because I don't want to wait for all these augmentations to be over. And then I'll basically just enter here what times I see in the L4 environment, and I need to apply scaling factors then. So for example, if I use the ARC2 evaluation data set, which only has 120 tasks, I need to double my actual time that it's going to take in Kaggle. And that's why I've got this factor of 2 here. And this allows me to estimate then, for example, here, I think I'm going to take 9.43 hours for training, and then 0.82 hours for inference. And actually, this is good information as well. I didn't address the split between time you spend training versus eval. As you do more augmentations, you improve your score. You can see that just now. What I'm doing is not correct because these pass at 1,000 or pass at 100. This is where you are, yeah, you're basically using 1,000 augmentations, ranking everything from 1 to 1,000, and now you're looking at pass it to 500, 1,000. That's actually different than if you use varying number of augmentations. All of these graphs here are at fixed number of augmentations, but just considering different passes on that 1,000. What I'm actually considering is varying the augmentations, which is something different. But the direction is the same, which is that more augmentations will give you better score, but it asymptotes. So these graphs are not exactly relevant, but basically if you run augmentations of 256 versus 512, you won't see much change in the score. So I'm probably fairly optimal around the number of augmentations. I probably could even go to 128 without much penalty. And I'm only taking about an hour for doing the evaluation. So, you know, I felt I'm spending most of my time in training. My augmentation, I could make it longer by doing more, but I'm probably asymptoted. So there's not going to be a huge amount of benefit to going much further in terms of spending eval time. Now, if you had a bigger model, that would change things because a bigger model is going to take longer time to evaluate. So you're probably going to have to spend more time in evaluation, and that's going to restrict your training time. And anyway, the model is bigger, so you're going to get less optimizer steps. So you're going to have even less optimizer steps. So these are some of the trade-offs you'd have to think about if you want to make the model bigger. But yeah, I wouldn't rule out that a better model is still better. Okay, let's go back to the notebook here. So I have this parameter here where I freeze the trunk for 1/4 of the epochs. I don't have high confidence on how much it should be frozen for. Maybe no epochs would have been fine as well. I disable weights and biases. Now I've one little extra snippet here that technically allows me to run on T4s. Now I realize this was a bad idea. It's a bad idea, but then a good idea. It's a bad idea to run it on T4s. It will run. So you could turn this on. You could submit it here and I would put T4 submission. This is a good idea because L4s are in very high demand often and you have to wait hours for them. So if you just want to check it all runs, it's handy to be able to run on T4s because you know it works on CUDA. But you definitely don't want to submit that because it will still run on a T4 and it will run out of time, which is what happened to a number of my submissions. So this functionality here really just allows me to run a T4 for a quick check, but I need to make sure that when I actually want to submit, I go to L4 here, and then I'll save an L4 version here, and I'll save TRM, and then whatever epochs I want. So yeah, then you'll run it for the session, then it will queue. Once it's done queuing, which may be quick or slow, it'll run, and only then when it's run are you able to press submit. And the submission itself, which could take 12 hours, needs to complete by the deadline. So that's why you basically needed to be saving your submission early Monday morning. And as it turned out, even that wasn't enough because there was a queue going until like midday. And by midday, there's no way that your 12-hour submission is actually going to run. So probably the last chance really to submit was somewhere really early morning Irish time on Monday for the midnight deadline. Okay, so next I have, I mean, this is public. There's a copy now in the GitHub repo. But yeah, there's a bunch of issues around CUDA and PXTAS that I had to work with ChatGPT to get through. I didn't dig deep on understanding, but once I kind of got this here, it kind of allowed me to get through. Next, yeah, this is not a very long notebook, by the way, but there's two more steps. One is we need to build a data set. So we're going to build a data set with the test tasks right here using build arc data set. And then we're going to load a configuration file for the training, which I'll talk through in a second. And once we have that configuration file loaded, we will run the training. And the training itself, the TRM training, includes the evaluation. So that's nice. At the end of training, you've got the submission file ready. It actually does evaluation and makes a submission file, which is beautiful. You do not want to evaluate at midpoints because that's just wasteful in terms of compute. So you only evaluate at the end. And once you've evaluated, it'll create a submission file. And the very last thing then is you need to make sure the submission file ends up in the Kaggle working directory. So you have to copy it from where the latest submission file was created into the working directory, and then you're pretty much done. Now, there's one other thing which maybe as well I'm just doing suboptimally, but you need to have installed all your packages like PyTorch, etc., but you're offline. This is all an offline competition running on GPU. So how do you install all the packages? And one way you can do that is by using a script. What a script is, a utility script. It's basically another notebook that runs all of the installs. You can actually see it here. I've called my one ArcAGI 2025 aux. And this one here will just clone my GitHub repo. And when I say my, I mean the tiny recursive models fork, the Trelis fork. So we'll fork it, and then it will clone one of the branches. So I had it private. It's public now. You can just take off the private part. And it will do the installations. So yeah, you basically need to set up the installs. And yeah, there were a bunch of NumPy issues that I ran into. Often the base system version of NumPy is different to what later gets installed through the Torch installs. And that particularly clashes with SGLang, which is not relevant here for TRM, but is relevant when I was running Python program generation. So anyway, I won't go through this in detail, but suffice to say, you install here online so that you've got all the packages, and then you import that so that it can be used as a utility script here for when you want to submit. Now, I'm going to talk about the configuration file. There are basically two key files in TRM. If you want to understand the TRM repo, you just have to look at two files. The first file is the pre-trained configuration, and the second file is the architecture of TRM. And I'm going to go through both of them in the repo. Here, what I do is I just make a configuration in a cell that mirrors the config file. I call it config.yaml, and I feed that in when I want to run here. And I don't change the architecture explicitly. I'm loading the architecture from the repo. So you can't see everything here, but what's happening is the utility script is loading all the packages, but it's also actually loading my repo, my forked repo. And that forked repo then is being accessed, and a command is being used in order to run the training script that's in that forked repo. So we're going to come back to this Kaggle description, but I want to walk you through the pre-training now, and I'll go through as many steps as I can. So let's go over to VS Code and start to take a look at the forked repo. Now, you can find tiny recursive models if you go to GitHub/Trelis Research, and then go to /tiny recursive models. You can clone or you can fork the repo yourself. And what I've got here is a one-click affiliate link, which I already clicked when I was showing you the L4s. But what it allows you to do is very quickly run and do pre-installs. Yeah, do pre-installs that you need. If you just clone the original TRM repo, the most common problem you're going to see is that it uses Atom ATAN optimizers. The optimizer is not standard Atom W. It's got some kind of a TAN adjustment. I'm not sure if it's in the softmax. Anyway, the Atom ATAN library gives issues, and you need to replace it. Well, you don't need to, but one solution is to replace it with Atom ATAN PyTorch. So yeah, actually, with the help of Jack Boylan, who helped me to run the pre-training, he replaced Atom ATAN PyTorch in for Atom ATAN, and that allows it to run smoothly. So I'll show you the onStart command here in the template in a second. But first, let me just say a few things about the GPUs. So if you're going to train, these are small models. You need to have high flops as high as possible. And the more GPUs you have, the faster you can go. You can run them in parallel, you can run multiple nodes, and you can select that in the start command. But actually, the most powerful GPU, the B200, which is 569 an hour, and the H200, which is 359, they both actually have very similar flops to the H100. SXM, by the way, means that you have multiple on the same chip, so they're connected with very high speed. So while I was training with these initially, I quickly, well, not quickly enough, I realized these all have the same flops. And so it's far more cost efficient to train on the SXMs. So ideally, I would train on 4 of these to mirror the 4 I have, the 4 L4s, and also the 4 that Alexia used. But to go faster, sometimes I would train with 8. if you train with more, to use the CUDA cores, you need to increase your batch size. You need to increase it proportional to GPUs. And if you increase your batch size, you need to increase the learning rate. The heuristic is if you double your batch size globally, you should double your learning rate. And I'll show you that in the code. That may have adverse effects on the training performance, though. Another heuristic is that the smaller the batch size, the better the performance, because it adds favorable regularization. So it's hard to know if those results I showed you in the paper towards the end, what did I show? I basically showed that these later ablations where I ran for longer, I did run those on 8 GPUs with larger batch size. So that might be another contributing factor, that my batch size is bigger. Now, I did post-training ablations where I used smaller batch sizes and I didn't get improvements. So it's really hard to know. A lot of this, I can't overemphasize how there's so much noise in results that I've seen. And yeah, even in my write-up, I tried to describe everything, but I should emphasize that there's just a lot of noise, and I definitely don't rule out that people could do way better with stuff that looks similar, or by doing a change here or there. I think that's definitely plausible, and I don't mean to say that there are limits just because I got a certain score. That doesn't really say much about how far you could take this approach because of a lot of the noise. Okay, so I recommend H100. You can use NVL or PCIe, but they're a bit slower, these ones here, because of the interconnects between them. So you can see some different. Yes, sorry, I'm slow, Jarvis, to put that up, but it's already public. And I'm going to go through it right now. And it's in the main branch of the repo, which is, it's this one here, github.com, Trelis Research, and it's tiny recursive models. Here we go. So yeah, you can clone or fork it. That's the one I'm actually working on right now. Okay, so in RunPod, you've got your GPUs. The H100s are not always available. They typically be available in the morning in Ireland, so I try and start runs then, and then I click deploy. Now, I've actually started a pod already, and I've started a H200 because the H100s weren't available. So I would sometimes do that for shorter runs. And yeah, you can see the start script is finished and it's running. And here is the start script. So it does a few things. It exports some useful variables that allow me to grab private models, that allow me to log to weights and biases. So you do need to set these in your secrets if you're using RunPod. Sorry, my screen's back now. It updates apt-get update, and it will then CD into the workspace, which is the default folder on RunPod. It will clone tiny recursive models, fast forward if it's already cloned, and then it will run init.sh. Init.sh is a script put together by Jack, which you can find here. And this will go through all the setups, including installing the Atom ATAN2 PyTorch, which is what I described already. And then it will set all the environment variables. So if you get to the point, and you shouldn't have to do anything other than set your secrets, which by the way are over here, and there's instructions on setting the secrets if you look at the README. So if you look at the README here, does it say it in the README? Yeah, you need to set these things. Optional, but recommended. If you get this far and the pod is up and running, just check it says start script finished. You then go to connect, copy, and then you go to a terminal. And you need to have an SSH key set up so that you're able to copy paste into the terminal. Let me show you here. So here, and actually my key is RunPod, so I need to change that. And now I'm SSH'd in. So if I ls here, I can move to workspace. And in workspace, I've got tiny recursive models. So I'll CD into that too. And yeah, so here I should have all the files that I need. From here, I'm going to be able to boot up training. I'm going to show you pre-training, then I'll show you post-training, and I'll comment on how to do continued pre-training, and then I'll go back to the Kaggle again. So you can actually see how I ran the final runs for the last submissions. And for any pre-training run, you need to do two things. One is you need to you need to prepare the data set, which means taking the raw tasks and generating augmentations and task IDs. And then you need to run the training. So there are two parts here. I'm going to call this pre-train all to 100, and I'll just say demo. So we're going to train for 200 epochs. I'm going to switch to the meta branch. That's actually not needed because I've merged it into main. Git pull, and then run the build Arc data set. Now, we're going to pull from the Arc combined Arc AGI folder, which is here. It's where the data sets are. And you'll see that there are the original data sets, but also there are data sets that I've added. So I talked earlier about the clean data set. This is the evaluation 2 data set minus the 6 tasks that are also in Arc AGI 1 eval. I've also got some splits here where I've split eval into 3 even sections of 40 tasks each. I've also got a training hard split, which is 120 difficult Arc AGI 1 training tasks. I've also got Simon's Tama split here of 50 tasks. I've also got roughly 23 manual tasks that I made, which are kind of the concept versions of some of the hard Arc AGI 2 eval tasks. Anyway, you can decide to choose which ones you want for training. The baseline training, by the way, that Alexia did would have been this. So it would have been concept, training 2, and evaluation 2. So let's copy that. And the test split, specifying the test split here means that only the train examples will go into the training and the test examples will be used for evaluation. Whereas if you put the subsets here, it means the training examples and the test examples will be used in training. So you're actually training on most of the, well, all of the train and test splits here. So here we're going to build a data set. Let's actually do that. Now, it's going to take about 10 minutes to build if I build with this much stuff. So I'm going to reduce that and just build with evaluation 2, which means the train examples will go to training and the test will go to test. So let's go here and, ooh, sorry, I actually don't need to pull the ands. So it's done git pull and it's going to build a data set. It's instructive to look at what the logs are saying here. So I'm just going to wait for a second. All right. So it's generating up to 1,000 augmentations per task. And what this is telling me here is that for puzzle 7.1e, there's actually only 576 augmentations. Why is that? Well, it's because every puzzle, if you look at all the flips, rotates, there are 8 maximum possible flips rotates. Some will have less if they already have symmetries. Then there are a much larger number of recolors because any color you can map to another color. Depending on how many colors are in the task, you can have quite a large number, like well over 1,000 of those. So some tasks, depending on their symmetries and their color patterns, they will be limited. Like this one has actually reached a max of 72. So you can't generate 1,000. But all the other tasks, it seems, of which there are 118 other ones here, because it includes the 6 that contaminate. Those have clearly got at least 1,000 augmentations. So we've got 120 puzzles and we've got almost 120,000 augmentations. And that's the number of rows of data that's going to be used for training. So we have that now. And next, what I'm going to do is run the training. So to run the training, I'm going to run it on the number of nodes. I've actually only got 4 nodes here. If you go back to run pod, sorry, not nodes, GPUs. Expand. See, it's small, but it says H200 multiplied by 4. So you can't really see it too clearly, but it's 4 anyway. So that means I'm going to put in 4 end number processes per node. You can run on multiple nodes, but I'm only on 1 node. And we're going to run pre-train. And we're going to point to the dataset path that we've set up here. So this needs to match. We're going to use the TRM architecture. Oh, sorry, you can't see my screen. Okay, that's better. So sorry, I've got 4 nodes, sorry, 1 node, 4 GPUs per node. I'm running pre-train. I'm using this configuration file, which we're going to talk about. I'm using this architecture, which we're going to talk about, TRM. I'm pointing to the data path that I've set up here. and I'm running with this run name here. So yeah, let's get this running. So I paste it in here, and I'm then just going to tail this log here. So tail-f, and we're going to see the process start up. Now, before that starts up, let's take a quick look at this configuration file and the architecture. First thing we'll do is look at the architecture, which you can find in config and then arc. And this repo actually originates from the HRM paper, the hierarchical reasoning model. So it has a few different architectures, but the one we want to use is TRM. So I'm going to go through what these all mean here. First, we've got the loss. We've got the name of the loss type, stable max. It's not just a soft max. Now we've got some hyperparameters for the halting head. So the model's got embeddings. It's got a trunk that predicts the output grid, but it also predicts if the output is correct. And what we want to do is spend time on problems that are not halted. So we want to spend more time on the harder problems, but we still want to explore some of the easier problems where we have halted. And that's what the halt exploration probability does. It's saying, I think 10% of the time, or it's roughly a weight that's going to say, okay, we'll focus on the hard problems, but actually sometimes we'll just spread broader and repeat some of the easier problems for diversity. The maximum number of outer loops is 16. Halt max steps eval. Yeah, I put in this parameter so I could have a different value for evaluations if I wanted. So I could allow 16 outer loops at training, but less during eval, or more. Actually, more would be interesting. Solving Sudoku with HRM or with TRM either, you do better if you just use more loops at inference time, which is an interesting idea for Arc2, and I tried it, but it doesn't really help. That's probably another area for further research. Puzzle embedding dropout, grid token dropout, grid noise probability, grid noise fraction. These are all new parameters I added to allow you to add noise during training. Sometimes adding noise helps regularization. In hindsight, I regret adding this just because the results are so noisy already that adding noise makes your results more noisy and is very difficult to ablate. I wouldn't rule out that adding some types of noise probably help or drop out, but I wasn't able to conclusively ablate that. Next, we have the upper cycles, which for clarity on TRM, they occur on the same neural net. You have 2 layers of cycles. Upper is 3, lower is 4. In the paper, it uses 6 lower cycles, but everywhere else people have replicated as 4. A bit unclear exactly why that is. Number of layers, there are no H layers because it's a single layer model. In HRM, there's 2 different neural nets, and the number of lower layers is 2. The hidden size, this is the key dimension for the trunk, is 512. Number of heads, this refers to attention, is 8. The expansion factor in the MLP is 4, so it goes up to 2048, I believe, and back down to 512. This here is the puzzle embedding dimension, which defaults just to the hidden size. This is interesting. Basically, the HRM has a ton of model parameters in the embeddings. There's a 512 parameter vector for every single task and its augmentations. So that means you've got about 1 million tasks, including augmentations, in the pre-training that each have a 512 embedding, whereas the model is only 7 million parameters. So you have like 500 million parameters in the embeddings, and you've got 7 million in the model. So I don't know. It seems to me like there are way too many parameters in the embeddings, but I don't know. I wasn't able to fully ablate it. Next, position encodings use rope as opposed to, say, sinusoidal or something. Brain float 16, which is supported on the L4s and also H100. This here is if you want to use just MLPs for L instead of transformer, but we want to use a transformer because Alexia finds that better in some ablations. Puzzle embedding length, this is actually 16. Now, I changed it to 1. Probably it's confusing if you change it to 1 because the paper uses 16. However, what this sets is it says that every embedding is going to be the hidden dimension. And if the embedding dimension allows for multiples, it's going to use up to 16 of those. And because the puzzle embedding dimension is equal to the hidden size, actually only the first of those embeddings is used, and the other 15s are actually zeros. So this is kind of weird, but clearly the intention of the model was to allow for there to be multiple embeddings representing each task up to 16, which would be even more parameters because it would be 16 times 512. But actually only one of them is used because puzzle embedding dimension is equal to the hidden dimension. So you just have a bunch of zeros. Now that's not a big deal. There's very few parameters in those positions, so it probably doesn't really affect the model that much. But it's a bit weird to have it at 16 if only really the first one is being used. Anyway, it's probably a bad idea that I changed it just because it's the thing that you're classically going to forget when you come to tuning, and then you're going to have a mismatch between a model you reload for post training. So yeah, I don't know, it probably wasn't ideal. And then no act continue. There was originally in the HRM paper, it trains two heads, one for whether it should stop and one for whether it should continue. And if the stop goes above the continue, then it stops. Whereas in the TRM paper, it just uses one head. So you want to set this to true because the TRM paper is a bit simpler. And I think just as effective. So this is TRM. If you wanted to ablate a bigger size model, this is the obvious thing to do. Change this to 1024 for bigger, or for smaller, 256. If you want to change the embedding size to something smaller, 64. I did some quick ablations with different embedding sizes, but I just wasn't comprehensive enough to really take anything away from it. So if you wanted to increase the number of cycles, you can do that in a few ways. You could do more lower cycles. You could do more higher cycles. You could also do more outer cycles up here by changing the 16 to say 64. So you could have, this would be a really big effective depth. It would be 64 layers. Well, 64 times 8, and it's actually 8 plus 1 because it's like all the L's followed by 1H. So it'd be 64 times 8 plus 1, 64 times 9 times 6. So that would be a lot of effective depth, which may help with ARC. It's hard to know, but that would be another obvious direction to ablate. So yeah, like broadly, things I would think are interesting are doing a $1,000 run on doubling the hidden size, doing a $1,000 run on half the hidden size, doing a 1,000 run on doubling the number of cycles, maybe by doubling the halting steps, or maybe just by doubling the L cycles, and also changing then the ratio of the puzzle embedding dimension, making that smaller. I mean, that's my intuition, but maybe making it bigger too is worth ablating. So those are the TRM parameters. Then there's the configuration file. So going back here to the run command, which we'll go back and look at in the terminal, there are two things you need to control. One is the configuration file. The other is the architecture. So here's the configuration file. It defines the architecture. You can set the entity for weights and biases. You can set the data paths, but you can see that I've actually set them here explicitly within the command. And if you don't set the one for the past test paths, it will default to just the path that you specify. Don't put this as null though, because that will cause an issue. It needs to be brackets here, in which case it will pull from data paths. Here, if you want to do continue pre-training, you can load from a checkpoint. This is relevant if you want to do post-training or continue pre-training. I didn't change anything on evaluators. Batch size. So default batch size for training in Alexia's paper is 768. And by the way, I'm actually looking at the post-train config, which is not what we're doing. We're actually running the pre-train. So I should really be looking at pre-train all, this one here. So I've saved copies so I can point to them. What was I talking about? Yeah, batch size. So the original was 768, but because I was training on 8 GPUs, I would double that. Now I'm actually on 4 GPUs, so this might have gone out of memory actually. Did it go out of memory? Actually looks good. So maybe you can fit with that larger batch size. That's good. But broadly speaking, more GPUs, you want to double your global batch size to use the CUDA cores properly. And if you double your CUDA batch size, you need to increase your learning rate. So the default in the base repo is 1E-4 and 1E-2 for embeddings. But if you double the batch size, you want to double the learning rate as well. Warm-up steps default to 2000. I didn't change that. I didn't change the betas or the weight decay. And yeah, there's a weight decay for the puzzles. And yeah, so this is interesting. The learning rate is way higher for the puzzle embeddings, compared to the trunk. And I assume the motivation, which probably comes from HRM rather than TRM, is that there are 1,000 augmentations per task, and there's an embedding for each of those augmentations. So on each epoch, the data loader samples from one of those 1,000 augmentations for each task. You are only seeing each embedding ID one every 1,000 tasks. So you think, wow, that's a lot of epochs if you run 100,000 epochs, but it's not really. It's really only like 100 epochs from the embedding standpoint, because they're only being seen once every 1,000 epochs. So I assume that's why they have to use a higher learning rate here when they do the puzzle embeddings. But yeah, I don't know. It's kind of a high learning rate. And then conversely, it's kind of a low learning rate here, 2e minus 4 for a model that's 7 million parameters. It's a tiny model. So I don't know. There might be some ablations that make sense there. And here we have the exponential moving average, which apparently gives a relative roughly 15% boost, according to the TRM paper. So I've left that on. And here are the parameters for freezing the weights. If you want to freeze the trunk, you set that to true. And then you can set the epoch where you unfreeze. So you can unfreeze at some point. These are custom coded by me. Well, this one is default here, and this one is custom coded by me, so I could unfreeze. Okay. Quick question. Yes, this is nice. I ordered GB10 and arriving nice. Can it be run with FP4? Well, FP4 is relevant for Blackwell. I'm not training on Blackwell. Yeah, it would be really hard to try and think about doing that. It could be done, but you'd have to re-architecture things a lot. And the L4s don't support L4. And Simon is saying, so tasks can be scaled up by 2 and 3x. Do you mean augmentations? Or do you mean the raw tasks? And if you mean the raw tasks, what data would you include? I'm curious. I did some ablations increasing augmentations, but if you're at 1,000, you're probably covering a lot, given there are only 8 dihedral groups, G4, and the recolors, maybe you're not covering every recolor, but you're kind of getting a lot of combinations. I reckon the augmentations are maybe not a big lever, but since I haven't tried it, it's hard to say. Oh yeah, nice. That's cool. So turn each one. Yeah, that's nice. Basically take a small grid and then you can use it as a big grid. And that's isomorphic, I think, if that's the right word. So that's quite a nice idea. There's maybe some ideas around shearing. I don't know, my dad had mentioned shear, like, why don't you shear some of them? It would like change it, but maybe it adds some information. There's also some patterning ideas. By the way, the augmentation approach is very solid within HRM and TRM, and it's nuanced what it does. So when I say augmentations, it will randomly sample from the dihedral groups, so the rotates and flips and the recolors, and that will become a distinct augmentation. But additionally, but not as a separate augmentation, when it takes a given augmentation, it will randomly transpose it or translate it across the grid if it can be translated. If it's 30 by 30, it can't be translated, but if it's anything smaller, it will randomly all of the grids will be translated by the same amount, and that is built in. So you don't get a separate augmentation for the translations, but any given augmentation is going to be randomly translated. Now, it could be interesting to turn that off as well and see if that leads to better or worse performance. But yeah, it's just pretty solid how they've thought about augmentations, and I suspect that perhaps a good bit of performance, at least at the level that that the TRM paper is at, and possibly last year's winning approach too, comes from just having solid augmentations. Okay, so we have got training up and running. Let's go across. Okay, nice. So the training is up and running, and it's projecting 6 hours. It's fairly fast because I'm only training on 120 tasks. What else? It's actually completed 1,000 steps, and it's moving to doing inference here, which is doing in batches. And probably at this point, I have started up a weights and biases project, which I can maybe find. It might have produced a new project because I did I change the dataset name? I don't think so. It's actually here. It's in with my final pre-training. And you can see the demo. And you can probably see the loss. Let's see if we can find the loss curve here. Yeah, I'll just zoom in on some of the first steps. So here, yeah, it's kind of interesting. It's using a much smaller data set, but the loss curve is somewhat similar to my data sets where I've used a full, I've used training data as well, which actually would be, it's not that one. It would be this one here, the blue one. So my loss is, it's a little bit different. It's a little bit different. It's actually a bit sharper when I'm using the smaller data set. I would expect it to be more similar to the pre-train hard, which is actually a filtered down set of eval tasks and hard training tasks. I don't know if it's that much. Anyway, the general pattern looks good. And we would soon, after eval finishes, we'll see a data point up here. It'll need to go through. So the amount of batches it needs to go through eval are going to be 1,000 multiplied by the number of eval tasks, which is 120, multiplied by the number of grids, which is an average of 1.5 test grids per task. So it'll be 1.5 times 120. So it's going to be 180 times 1,000. So it's 180,000. And then divided by batch size, which is 1,300. So you need to divide those numbers. And that's going to give roughly 180 divided by, I don't know, something like 100 and something over 100 batches, I think, in order to complete that. So it'll take a little bit longer and we'll get a score. It's early in the training run though, so probably we're not going to see anything correct. But if you let that run on, you'll eventually see it marked as correct. And what you'll also see, it'll save a checkpoint after eval. It won't actually save anything yet. So I don't think my checkpoints folder is even there yet. Oh, it is there. I'd say it's probably empty though. And I've got the name of the run. So this is where it's saving as PyTorch files. And yeah, it doesn't yet have any checkpoint.pt files, but it will soon once that evaluation is completed. It's still got a bit of a ways to go there. Which parameters Simon is asking for here? I actually don't know how to use TQDM, but that sounds like something I should be doing. So inference is ongoing, and I'm going to show you now post-training. So if you want to do post-training, you're going to need to load a model. You can do it on L4s if you want to simulate the test environment, but often I just want to do it faster. And so I'll do it on 4 H100s. And the difference with the post-training is you need to obviously build a different data set that you want to post-train on. And you then need to download a model. So I'm going to show you how to download the model. I don't know if I'll run the post-training. I will show you a few logs maybe. But in broad strokes, you repeat the same data set generation. You choose what evaluation split you want to use. Then you need to download the pre-trained model. These are all open source now. So if you go to Hugging Face, I need to find Hugging Face. Here we go. You can find all of the steps here. You can grab one of these points and you can just use the Hugging Face client in order to download the model. So if you run something like this here, HF download, and download it into a pre-trained directory so that when you run the pre-trained command here, what you can do is pass in the model checkpoint and it's going to load up the checkpoint and it will start training. And it's going to load up the checkpoint, initializing the embeddings to the mean of the pre-trained model's embeddings. So that's something just to keep in mind. In fact, if you take a look at one of the configuration files, which are basically the same as the configuration files for the pre-training, the only difference is, I think do I allow for setting? Yeah, there's this extra parameter, which you can also put in the pre-training configuration, but it won't do anything. You can set the embedding initialization to mean, or you can set it to, I think, normal. But what I found in quick ablations is that it's best to set it to mean. Normal means it would do a normal distribution over the prior embeddings, which is going to be more noisy. noisy. But yeah, I think mean, I only did quick ablations, but it seems to be better performing. And I'll just give you an example here, some of the hyperparameters, which should really mirror what you're doing in Kaggle. Everything here, I'm loading from the dataset path that I set in the start command. I'm setting my global batch size a bit lower because I can't fit 768, which is the original amount in Kaggle. I can only fit in the VRAM of 4L4's 384. Here is where you can set a lower eval global batch size. So this will still keep the original number of augmentations. And the augmentations, by the way, are set during data set generation. So you set that up here. It's not set in the configuration file for training. It's set when you generate the data set. But you can lower the number of those augmentations that are used during eval by setting this parameter here. So you could set it to like 256 or whatever the case may be. Here are your epochs. Here's the eval interval. If I was submitting on Kaggle, I would set this to the same as the number of epochs because I only want to eval once at the end. Checkpoint every eval, yes. So I saved the last one. Eval max augmentations. Sorry, I might have misspoke up here. Sorry, this is the batch size. This is the max number of eval augmentations, 516 or 256. You can additionally control the batch size. It will default to the number of augmentations, I believe. But sorry, it will default to the global batch size, which is here. But you may actually want to have a different eval global batch size. I ended up not using this, but I think you can find cases in Kaggle where you might be able to fit a larger eval batch size. Yeah, because during training, your global batch size is set by optimizer parameters and gradients, whereas during eval, you don't need any optimizer parameters. So you can fit a larger eval batch size usually than you can during training. So if you really wanted to, if you were up against, if you weren't fully using the CUDA cores, you might have a case where you want to increase the eval batch size in order to increase throughput. Okay, and what else do I have here? The learning rates. Yeah, technically, because my batch is smaller, the principal thing would be to cut into my learning rate here and my learning rate here. I actually ablated during post-training the difference and it wasn't very big. So I don't have a strong opinion on that. Everything else I've left the same. And my default was to freeze the trunk for 3,125 epochs, which you can see here, and leave on EMA. It's arguable whether you would leave EMA on if you're doing LoRa, if you're doing full fine tuning. Sorry. You do it during pre-training, so I just left it on anyway for the post-training, but I didn't ablate that fully. Okay, so it looks like evaluation was full there. I'll just take a quick look. I wonder if it scores anything. I doubt that it's scoring anything, but yeah, it's at 0. And the one to check is the pass at 1000 because that's the first one that's going to start scoring. But yeah, this is normal. Early on, in early epochs, you're not going to see any score, and then the score is going to go up over time. So yeah, that's a quick preview of how to run pre-training, how to run post-training. If you want to run continued pre-training, do I have a quick? Yeah, you need to download the model. So use HF download and make sure that you pass the checkpoint. But otherwise, you can just use the pre-training configuration file. Just make sure to load the checkpoint. Also, ideally, if you're doing pre-training, try to use the same data set. Don't regenerate the data set. If you regenerate it, even with the same command, the augmentations are at random, so you're not going to get the exact same data set. You may not even get the exact same number of task IDs because there is some randomness in when it tries to pick the augmentations. So what you need to do is when you're running training, you should push the model and the data set to hub, and then you should pull the data set back down again. And actually, if you look at any of the models I've pushed, after the first one I pre-trained, you can see that I pushed as well the data set. So you can pull down the data set from Hugging Face and put it into the data set folder. And I'll just very quickly show you here. If you want to push something up to hub, you can use UV run utils and then push to hf.py. And that's not going to work because you need to pass arguments, but it should show you the arguments. Yeah. So typically I would run this and then model dir. And what I would do then is I would grab the directory that my checkpoints are in, for example, this here. and then I need to pass the repo ID. And I do need to be logged into Hugging Face, which I am because my run pod on start command passed in my my token. But here I would do Trelis, and then I would do whatever the name of the repo is. And that's going to push it up. And then after I've pushed that, I would go back, run the same command, but I would backspace to get rid of the model checkpoint directory and instead just put in data, and that would push up my data set. So that's how I would push both of them. So yeah, this is, I discussed this in the paper. It's crazy how many task IDs there are in TRM. As I said, if you have 1,000 tasks and 1,000 augmentations, you have 1,000,000 task IDs, and there's a 512 dimension embedding for each of those. So it seems excessive. And yeah, I had the thought, is similar thought to Simon here, which is to create a task ID from a hash of the content of the augmented puzzle. I don't know, maybe that's what you're suggesting or not, but I'll just describe it anyway. And I do this, you can check it if you like. If you just go to this repo and you do git switch base-in. Oh, I've got some changes here. It's actually the paper. I can just discard these. So yeah, switch to base-in. It doesn't really matter that I switched because the branch kind of looks similar. But what I've done here is use the same task ID for every task augmentation. So if I have a given task, all the augmentations will get the same task ID. But I create a separate small embedding, which you could concatenate or add on an element basis to the existing task embedding, which is maybe what Simon is suggesting. I think those would be somewhat equivalent. But the other small dimension would represent two things. You could concatenate a small piece for the dihedral foregroup for those rotations and flips. And then you could encode a small bit for the color mappings. This branch here, it's going to be awkward to show, but what I've done is I've assigned a table for all the color mappings for the recolor pairs, and you can then develop an embedding basically for each of those pairs, and you can sum the embeddings for any color remappings that are in an augmentation. So if a given augmentation uses flip number 4, and then it uses recolor green to blue and purple to orange, you go find green to blue in that table, you find that embedding, you find purple to orange, you find that embedding. These embeddings are trainable, and then you either concatenate or add them, but somehow you add it to the recolor. Basically, you're making a little dimension, a little embedding that's going to capture the recolors and capture the dihedral groups. And this is going to be way smaller than assigning a unique embedding to every task. Instead, every task is just going to have its base task ID, and then the augmentation is represented by a little augmentation embedding. So yeah, I mean, this is kind of a thought that is reasonable, but it didn't improve performance. It was just worse. And I don't know if that's because the model is it's giving favorable regularization by including the embedding, by forcing it to learn different tasks independently. And the question that you should ask then is, well, is the model actually learning that these different augmentations are the same in embedding space, or at least related in embedding space? And one way I thought I might answer that, although maybe I'm missing something, is to look at here for some of these pre-trainings, look at the cosine of the angle between the embeddings. So look at the cosine within a task and between tasks. And let's just look at one of them first. So here, what you can see is the cosine of the base tasks between the base tasks. It's rising, but it's incredibly small. One interpretation of that is the model doesn't see that from an embedding standpoint, the tasks are similar. And maybe even more surprising, if you plot the embedding, the cosine between embeddings within task. So for the same task, look at the different augmentations and their embeddings. They're all really close to 0. Now, by the way, a lot of this is 0 just because every batch has not got 2 augmentations of the same task. It's got only 1 copy of every task. And that's why you're seeing a lot of zeros. You can see some small values here, but what I expected was that I thought the cosine would rise significantly within a task for different augmentations, because I thought the model would learn to kind of point, at least in some dimensions, the embeddings in the same direction if they're just augmentations of the same task. And I also expected that to rise a lot. And I expected there to be some rise in the cosine between different base tasks because there's some relationship between different arc tasks. Maybe no two tasks are the same, or maybe no two tasks are really similar, but maybe they're a bit similar. And so, yeah, this doesn't make sense to me and makes me think, well, maybe this interpretation is just wrong, or maybe there's a bug in how I'm measuring the cosines. But yeah, it's puzzling to me that the model seems to do better with an individual embedding per augmentation, and yet it's not obvious the model is learning that these embeddings are somehow related to each other. So yeah, that's a little bit unanswered, and it relates to the point that the embeddings are just huge in terms of parameters. Like, really, this is a 500 million parameter model if you include embeddings. The embeddings are just huge compared to the trunk, and maybe that's resulting in too much overfitting in the embeddings, or maybe it's resulting in a trunk that's not sophisticated enough. So yeah, there's kind of a lot of open questions, but also that points to the fact that if somebody did find one of those things to improve, maybe they would get a big improvement, because now maybe the model does learn that augmented versions of the same task actually are similar, and so the learning profile improves quite a lot. Okay, so I'm coming to the end here. I do want to quickly show the Kaggle submission, because it'll make more sense now that I've explained the post-training. And what I want to show you here is just the config file, which should mirror the config file I showed you for simulating Kaggle training. And yeah, we've got a run name, a project name. Weights and biases is disabled above, so the project name is not so relevant. We set here the maximum eval augmentations, which is 256 set above. I did need to reduce the number of workers, and I'm not actually sure if I had a problem with this being higher, but sometimes you need to set it lower. Oddly, when I was running on Lambda Labs, because I had a small amount of sponsorship for them for pre-training, I needed to set the data loader workers, or else it wasn't running the pre-training. So just keep that in mind if you're using Lambda Labs. Global batch size is being passed in here to the config. 300 and what is it? 306, 300 and where do I set it? Global batch size, GBSC, 384. Yeah. And what else? Learning rate 0.5. It's cut in half because my batch size is half. Puzzle embedding is cut in half compared to the baseline of 1e minus 2 because my batch size, global batch size is half. 2000 warm-up steps. And yeah, frozen epochs for a quarter of the epochs. I'm freezing the trunk and just training the embeddings. So I'm trying to get the embeddings to fit the trunk first before I train everything. And you can see up here, it's using the TRM config, which means it's just using the configuration that's specified in the TRM file right back here. I'm in the wrong branch here now, but if I went back to git switch main, it's using just the TRM file. And I'm going to show here. Yeah, it's the exact one I've shown you for pre-training. So there's no change between the pre-training and the post-training in terms of the architecture, which makes sense because you're trying to reload the same architecture. So it's just this file here. And yeah, that's pretty much the submission. There's one other thing, which is that you need to import the model because you're going to load the model. And to load the model, those again who've submitted will be familiar with this. You need, well, this is one way to do it. I think you can just upload it as a data set, but the way I did it was I have a notebook called TRM model, and I have a very simple script that downloads from Hugging Face. It'll just grab a specific checkpoint here using HF download. When you run this and save it, the notebook will then save with outputs. So if I look at one of the output versions of the notebook here, let's check, open it in the viewer. The output will actually be that step. This is the 2.5 gigabyte model. And then when I go to data sets and I go to my data sets, I've got a TRM pre-trained data set, which I can then update by doing new version. And by default, I created this data set pointing to the outputs of that notebook. So when I update it, it will give me a new version of that data set. I'll create or update. And now I have a data set that I'm able to import into my submission, much like the utility script. I just add it here and I can refresh it as well. There's no updates available now, but if I change the notebook, run it, save it, then update my data set, then update here. I'll now have my latest data set in the Kaggle notebook. So you can see actually there's quite a few steps in just submitting to Kaggle. And even if you want to do one spin around, that might mean you need to update your core libraries. You need to run your auxiliary script. You need to save your model, download from Hugging Face, save that script, update the data set, import it here and update. Then you need to rerun here, save the submission. So pretty easily you can spend an hour just kind of doing a basic submission. So yeah, definitely I underestimated the difficulty of even getting a blank submission, scoring 0 through. And that's not to mention that when you submit, you do not get any feedback about why it crashed, because if you did, it would be a way that some of the results or information on the task could leak. So if a submission fails, and you can see here, I had a ton of failed submissions. Let's go back. Not recently, but when I was doing a lot of work on the SOAR model, which I'll talk about tomorrow, which is a Python program writing approach, I had so many failed submissions, which was largely because I was running out of memory trying to run Python programs, which I'll talk about tomorrow. But it was very difficult to debug because you don't really know exactly why it crashed. And then, yeah, you need to think about replicating it maybe on L4s on RunPod. Now, Simon's a lot more experienced than me on running these things. He does git clone inside the notebook, so he doesn't have to click on the button. Yeah, that's cool. I bet you there's a ton of little tricks like that. If I hadn't been doing it first time, or if I'd been more attentive to reading more blog posts, I probably would have found a few more speed ups. Okay, any more questions? That's it for today's session on TRM. You can find, I'm going to put some links into discussion here. I'm going to link a post by Guillermo, who's up there on the leaderboard. This covers some Python writing approaches, which I'm going to talk about tomorrow. I'm going to link the ArcAGI2 paper, which I hope to get soon on archive, but you can get it available here. I am going to see if I can find Simon's data set. Here it is. This is the Tama data set. Thanks for your questions and input, Simon, and help discussing Tama as well. There's a lot more work that Simon has done you can check out. I do want to thank RunPod as well. I'm going to put the affiliate link here in the chat. Many of you already have access to compute. I think there's some small bonus if you do sign up with that affiliate link. RunPod sponsored 15,000 worth of compute, so not insignificant. And that's definitely appreciated. Helped a lot with the pre-trainings. Any other questions I'm happy to answer. Otherwise, I'll be back tomorrow. It's going to be same time tomorrow at 2 o'clock. I'll be talking about writing Python, which was a lot less successful as an approach. In some ways, maybe it's more interesting. I don't know. TRM was very interesting too. And I suspect that as more details come out on the winner solutions, there's probably a lot more insights than those that I came across. All right, folks, that's it. That's it for this week, or rather for today, because I'm going to be talking again tomorrow. Appreciate everyone joining. Thanks very much.